Hello everyone. Tonight we're going to explore many different chemical elements, their properties, their abundance or their rarity, their relevance in everyday life. Some are very famous and others are little known, but they are all interesting to discover. I will also tell you about the periodic table of the elements that we are going to follow and detail in our systematic exploration. And I will explain plenty of other things about what distinguishes elements, their atomic structure, how and why they combine to form molecules and chemical compounds. We will see where they are found and how they are used in industry or research. So we have a lot to discuss. So much that this story is going to be in several parts. Tonight we will cover elements 1 to 12, from hydrogen to magnesium. And we will continue our review in the next episode. Now, please make yourself comfortable. If you would like to try a different take on science stories like this one, you can already find some on Lights Out Library and La Biblioteca de los Sueños, which are podcasts and YouTube channels with my stories retold by Olimpia in American English and in Spanish, respectively. You will find links to them in the description. As always, I also invite you to listen on Spotify, Apple Music and other audio platforms if this is more convenient for you. And you are also as welcome as ever to support this channel on Patreon. It gives you access to downloads. You can stream all stories too, with or without background sounds. And it really helps keep me going with new stories, because I try to minimize advertising on all platforms, as much as YouTube lets me, at least. I also avoid sponsorships to not force more commercial pressure on you with products that I'm sure you don't need. So I rely on your voluntary support to fund this channel, if you wish. And now, let's get started with the first element, hydrogen. Hydrogen is thought to be the most abundant chemical substance in the universe. It certainly is in our galaxy. It is estimated that roughly 75% of all matter in the universe would be hydrogen. And this element could be called the simplest of all of them, because it is the lightest and its structure is simpler than others. What does it mean? To understand what a chemical element is, we need to talk about the structure of atoms and what makes an element different from other elements. As you know, all atoms have a nucleus made of at least one proton, a smaller particle. Another type of particle, very similar, that are also found in this nucleus are neutrons. And to this nucleus are bound one or several electrons that change place very fast and form like a swarm around this nucleus. This is what an atom is like, and what defines an element in the periodic table is the number of protons in its nucleus. This number of protons is called the atomic number. Hydrogen has one proton, so its atomic number is 1. If it had 2, which happens when two atoms of hydrogen merge, when they fuse, it would no longer be hydrogen, it would become helium, the element with the atomic number 2. As you also know, atoms are not the smallest possible units of matter we know of. They are made of smaller particles. We just talked of protons, neutrons, and electrons. And these particles are themselves made of even smaller bricks, smaller units. Atoms can gain or lose particles. They can be broken sometimes, or forced to merge, even though it takes a lot of energy to do that. So they are far from being a primary unit of matter. They are made of different, smaller bricks. So what makes the atomic level that relevant in that case? Why do we look so much at atoms when we speak of matter? First, because atoms happen to be a very frequent and stable type of organization of matter. Not all of matter is organized, structured in atoms in the universe. There are also free particles, but the bulk of matter we know of is structured in atoms. And another thing that makes atoms very relevant is that all elements appear with the atom. Under it, when subatomic particles are not structured as atoms, there are no elements. All the elements we know of, from hydrogen to the heaviest atoms, have certain properties that distinguish them because they are structured as they are as atoms. Hydrogen, gold, iron, or uranium are made of the same basic particles. They are differentiated and have these different properties, including their appearance, their mass, their capacity to react with other elements, only because they are atoms. This is actually how an atom is defined. Atoms are the basic particles of chemical elements. We will see a lot more about atoms and how they interact. But to go on with hydrogen, why is it the most abundant element in the universe? It is believed that the early combination of particles into atoms after the appearance of our universe, after the Big Bang, created essentially hydrogen atoms. The formation of protons, which are the nuclei of hydrogen, occurred almost immediately. It is believed in the first second after the Big Bang. But it took much longer for these protons to get associated, to get bound with an electron, which made them electrically neutral. Both particles, proton and electron, are electrically charged with opposite signs. So when an atom has the same number of protons and electrons, it has no net positive or negative charge. It is electrically neutral. But at the start, just after the Big Bang, it is believed that matter was too hot for electrons to remain bound to protons. First, it needed to cool down. And only after this cool down, at a time estimated to be 370,000 years after the Big Bang, electrons and protons would have begun to bind and stay stuck together. So the first atoms would not have appeared with the universe itself, but rather a few hundreds of thousands of years later, when the original heat, the extreme concentration of energy, had receded enough for atoms to appear and remain stable. At first, all atoms would have been relatively light: hydrogen with 1 proton, helium with 2, and lithium with 3. All the other heavier atoms or elements with more protons, more particles in their nuclei would have appeared later and be the product of ulterior fusions between these smaller atoms, especially hydrogen. We will also elaborate on this later, and I will tell you how other elements would have formed. But why is hydrogen called like that, by the way? Hydrogen comes from Greek, and it means water former or water creator. The name appeared after it was discovered in the 18th century that this gas, because in standard conditions on Earth, pure hydrogen is a gas, that this gas could burn or explode and produce water when it was put in contact with air, more exactly the oxygen in the air. When something burns or explodes, it is in fact a chemical reaction. And this is what is happening here. The chemical reaction in which hydrogen and oxygen get recombined between them into a molecule called H2O, 2 atoms of hydrogen and 1 of oxygen, better known as water. Hydrogen got its name from it, its capacity to produce water when it reacts with oxygen. There could be a lot more to say about hydrogen, but let's move to a second element, the element with atomic number 2, with 2 protons in its nucleus, helium. Helium is not very present in our daily lives, contrary to hydrogen, which is a big component of our bodies. But don't underestimate helium, because at the scale of the universe, it is a big deal. About 24% of the total elemental mass in the universe is helium. I told you before that hydrogen was by far the most important one, with close to 75% of all elemental matter. So with these 2 elements, we already have close to 99% of the elemental mass in the universe. The bulk of matter consists of hydrogen and helium. Helium is very present in stars. It is the product of nuclear fusion in stars. You know that the fuel of stars during most of their lives is hydrogen. Inside the stars, under extreme conditions of temperature and pressure, nuclei of hydrogen atoms are forced to merge. And when they merge, this fusion liberates a lot of energy. This is what stars live on. And the product of this fusion is a new helium atom. An atom with 2 protons in its nucleus. So there's a lot of helium inside stars, and the more a star ages, the more helium it accumulates. Apart from stars, helium is also a big component of gas planets, like Jupiter or Saturn. On rocky planets, like Earth, Mars or Venus, it is present only in small quantities. At normal conditions of temperature and pressure at standard conditions, it is a gas that is light, colorless, odorless, non-toxic, and a well-known use of its lightweight is when it is used as a lifting gas in balloons or airships. Other than that, helium is used in different industrial processes. At a very low temperature, low enough to be liquid, it is used in cryogenics, the science of very low temperatures close to absolute zero. It also serves to cool electromagnets, to pressurize environments, or to make silicon wafers. Wafers in electronics are thin slices of semiconductors. The wafer serves as a substrate for microelectronic devices that are built in and upon the wafer. The largest reserves of helium on Earth were found in natural gas fields, especially in the US, which is the largest supplier of this gas today. One thing helium is famous for is that it is called a noble gas, together with other gases that are grouped with it in the periodic table: neon, argon, krypton, xenon, or radon. As we advance, I will tell you about the logic of the periodic table, because it is much more than a list of elements. It also tells us of their properties, and it groups elements between them. Noble gases are one of these groups. There are 18 different groups in total, and elements within these groups share similar properties. For example, all noble gases are odorless, colorless. They all become liquid at very low temperatures, and they are called inert because they have a very low chemical reactivity. They typically don't react with other elements. Why don't they? This is because of the configuration of their electrons. The number of electrons in atoms and the way the swarm of electrons around the nucleus is arranged is a big factor that determines reactions between elements. When elements react between them, which means new molecules or new compounds are formed or destroyed to be replaced with others, atoms share their electrons or gain and lose them. For reasons that have to do with the conservation of energy, atoms have a tendency to try to saturate their outer shell of electrons. Typically, the first shell, the first layer of electrons around an atom, has 2 slots for electrons. When there is only 1 electron in this shell, like for hydrogen atoms that typically have 1 proton and 1 electron, the atom will be prone to look for an association with another atom that also misses 1 electron on its outer shell. This is why a very common form of hydrogen is not independent hydrogen atoms, but rather dihydrogen, a molecule with 2 atoms of hydrogen. The 2 atoms share their electrons, which gives the dihydrogen molecule 2 electrons on its single electronic shell, and that is a rather stable association. Now the first electronic shell has 2 slots, and the helium atoms happen to have 2 protons and 2 electrons. So the atom doesn't need any association with 1 or several others to complete its electrons count. This is the reason why helium is inert. It doesn't search to react with other elements, because in that respect it is self-sufficient. Now the first shell of electrons has 2 slots, but the following shells have more. They have 8. And this is why there are other elements that are in a similar situation as helium. The following one is neon, which has 10 as its atomic number. 10 because it has 10 protons and also 10 electrons that make it electrically neutral. This means its first electronic shell of 2 electrons and its second shell of 8 are both full. This is the reason why neon shares a lot of properties with helium. In particular, the same lack of interest for chemical reactions, the same inertness. And the following noble gases in the periodic table, the members of the same group, argon, krypton, xenon, have this same characteristic. Their outermost electronic shell is full. They are not inclined to react, except under extreme conditions that never happen on Earth in our direct environment. And this is why these gases are used in applications when no chemical reaction is wanted. For example, they can be used to create an atmosphere around very reactive material, to prevent explosions or unwanted reactions. To mention just a well-known practical use of helium, of a noble gas that is not prone to reaction, I could mention the replacement of hydrogen by helium in Zeppelins. After the Hindenburg disaster, the accidental explosion of the Hindenburg, a German Zeppelin filled with hydrogen, as it was landing in America, in New Jersey, after a crossing of the Atlantic in 1937. Hydrogen was cheap and efficient as a filler gas for balloons and zeppelins. But it is also highly flammable, and it was only a matter of time before an accident would happen. Helium is very safe in comparison. It cannot explode or burn. Replacing hydrogen with helium didn't save zeppelins that still disappeared because they were too slow and not very cost-effective compared with planes. But if one day zeppelins return, it could probably be with a non-reactive gas like helium. Now let's move on to element number 3, our first metal, lithium. Lithium has been under the spotlight in recent years because it has turned into a strategic resource with the rise in demand for rechargeable batteries, a crucial component for electric cars in particular. There are several technologies for these batteries, but the ones using lithium are the most effective right now. Lithium is highly reactive, and it is always found either associated in molecules with other elements, like dioxide, or in solution in ocean water. But why is it so reactive? For the same reasons, helium is not reactive, basically. It's because of the electrons. Lithium has 3 protons, so it tends to bind 3 electrons with opposite electric charges. But we saw before, when I told you about helium and noble gases, that the outer layer of electrons was important for chemical reactions. Lithium has a first layer of 2 electrons, which is full, and on top of that, 1 lonely electron on the next layer, which could have up to 8. So this third electron is awkward. It can easily be lost, which turns the lithium atom into an ion, an electrically charged atom, because it lacks an electron. These lithium ions have a high solubility. They will mix easily with seawater, and this is why lithium can be found in seawater, but in very low concentration. To be exploitable in mining, it is found mainly in salt pans or salt flats, which are places where a salted water pool has evaporated, typically in deserts. The minerals found in these expanses of salt are much more concentrated than in ocean water, and from them lithium and other minerals can be extracted. This is why the biggest exploitable lithium deposits are in countries with large salt flats, like Chile, Argentina, Bolivia, Australia. A general rule when it comes to the quantity of every element in the universe is that the simpler and lighter atoms are, the more there will be of them. We have seen before that hydrogen and helium accounted for most of the mass of atoms in the universe. But even though lithium is also a relatively light and simple element, with its 3 protons, it is not very frequent, and actually less so than the elements that follow it in the periodic table. This sounds odd or paradoxical, but it is because the nucleus of lithium tends to be unstable. It doesn't take much for it to break, to fission, and lose one of its protons, which transmutes it into helium. This is why it is an exception to the rule that lighter elements are more abundant. Lithium is relatively rare for such a simple element. And lithium is also the first element of a family that has similar properties like helium was with noble gases. This particular family is called alkali metals, and it includes lithium, sodium, potassium, and bigger and rarer atoms like rubidium, cesium, and francium. Alkali metals are at odds with noble gases in a sense. Noble gases are inert. Alkali metals are very reactive. And the reason for this property is this one extra electron that makes them very prone to chemical reactions. So typically, alkali metals are not found pure in nature. They are associated in molecules with other atoms due to past reactions with them. And when refined, a block of alkali metal needs to be kept in an inert liquid or an inert atmosphere, because just a contact with the air could provoke a chemical reaction, a combustion. Our next element is beryllium, with atomic number 4, and it is another light element that is rare. It appears mainly in the core of stars when they approach the end of their lives. And when they do, they begin to fuse bigger elements because their hydrogen reserves are depleted. But this beryllium disappears quickly because it fuses into even heavier elements. On Earth, beryllium is quite marginal in Earth's crust, but it can be found. For example, it's a bit anecdotal, but there is some in some gemstones like aquamarines or emeralds. You now understand how the electron shells work. So beryllium has a first complete shell of 2 electrons, and on its second shell it has 2 electrons out of a possible 8 for this shell to be full. This makes beryllium and other members of its family, which also have 2 spare electrons on their outermost layer, rather prone to chemical reactions too. And actually, in natural conditions, beryllium is not found alone. It is always in combination with other elements, forming different minerals. This family of elements, headed by beryllium, is called alkaline earth metals, and it includes other elements we will review later, like magnesium, calcium, strontium or radium. Element number 5 is boron, another relatively rare element, which has a few industrial uses. One of the uses of boron is as a neutron capturing agent, in the nuclear industry in particular. But what does it mean and how does it work? Until now, I told you essentially about protons in the nuclei of atoms. Protons which determine the nature of an element and its atomic number. But there is a second type of particles that can be found in the nuclei of atoms, neutrons. Neutrons are a lot like protons, but without an electric charge. And for a given element, the number of neutrons can vary. A different number of neutrons means that properties are going to be slightly different, starting with the mass. For the same number of atoms, there is more matter if there are more neutrons. So, depending on the elements, there can be many versions of the same element, each version with a different number of neutrons. These versions are called isotopes. Typically, an element can have different isotopes that are not very stable. They have too few or too many neutrons, which will make them decay or turn into another element. So many of these isotopes are unstable, short-lived. They won't last. But many elements have various naturally occurring isotopes that can be perfectly stable, or stable enough to last a long time before they eventually decay. Boron, for example, has 2 naturally occurring isotopes, one with 5 neutrons and one with 6. The one with 5 neutrons is called boron 10 because it has 10 particles in the nucleus, 5 protons, this is what makes it boron, and 5 neutrons. And the version, the isotope with 6 neutrons, is called boron 11, 5 protons and 6 neutrons. But in total, there are 13 isotopes of boron that have been discovered, ranging from boron 7 with only 2 neutrons to boron 21 with 16 neutrons. But contrary to 10 and 11, which are stable, all the other ones vanish quickly. Those with a mass below 10 tend to decay into helium, and those above 11 turn into carbon, the next element I will tell you about. Now, boron is useful as a neutron absorber in nuclear facilities because it easily captures neutrons, and free neutrons are what produces chain reactions of fission in a nuclear reactor or a nuclear explosion. Heavy atoms that are prone to fission capture these free neutrons. This makes them unstable. They fission into lighter atoms and also liberate more neutrons that are available for ever more reactions. This is the principle of a nuclear chain reaction. Boron is useful as a mean of control. Because it is neutron hungry, it will tend to stop or poison, as is often said, the free circulation of neutrons that provokes the chain reaction. So it is useful to pilot a nuclear reactor, or in case of an accident, to capture and neutralize the flow of neutrons and stop fission reactions from happening. Now let's move on to a very important element, without which organic life as we know it would be impossible: carbon. Carbon has atomic number 6. It has 6 protons, and it is estimated to be the 4th most abundant element in the universe, after hydrogen, helium, and oxygen. In the Earth's crust, it is the 15th most abundant, but in our bodies it is the 2nd by mass after oxygen. Our bodies are made of 18 to 19% carbon. What distinguishes carbon from other elements is the number of shapes and compounds it can be found in. First, because carbon atoms can bond together in very diverse ways. As you know, diamond is pure carbon, and it is the hardest natural material we know of. But graphite, which is used in pencils, and that is soft enough to be used to write, is also pure carbon. The only difference between the two is how carbon atoms are arranged between them. There are other forms. Carbon can be shaped naturally or artificially into nanotubes or different kinds of mesh. These different arrangements are called allotropes. All elements can have different states. They can be liquid or solid or gas. Allotropes are something else. They are different arrangements of atoms. Atoms can be bonded together in different ways. So diamond and graphite are 2 allotropes of carbon. They both are made of carbon in a solid state, but their different arrangements, the different structure of carbon atoms, gives them very different properties. Apart from its allotropes, another remarkable property of carbon is its unique availability for the formation of chemical compounds under standard conditions. With its 6 electrons, 2 on the first shell and 4 on the second one, it has the capacity to form up to 4 bonds with other atoms. This property, plus its relative abundance, has led to a huge number of compounds with carbon existing. More than 200 million have been described and indexed. There are rather basic molecules and compounds like carbon dioxide, 1 carbon atom with 2 of oxygen, carbon monoxide, or all the hydrocarbons, which, as their name says, are compounds of hydrogen and carbon. But this is just the tip of the iceberg. There are also countless polymers, very big and complex molecules, in which carbon, oxygen, and hydrogen are abundant. All biological life forms we know of rely on carbon chemistry. And this is why even astrobiologists, people who study the possibility of life in other places than Earth, how it could appear, be disseminated, evolve. So astrobiologists generally believe that carbon would also be crucial to extraterrestrial life forms. Not out of a lack of imagination, but because of the chemical properties of carbon, this property to bind with many other elements in many different ways, and be used to build bodies as well as transport energy. Maybe a life form without carbon is possible, but it looks so much more likely to include carbon, and this comes down to the properties of this element that are determined by its atomic structure once again, and on top of that, its availability. As we said, it is the 4th most abundant in the universe. After carbon, we have nitrogen, which is number 7. Nitrogen is another abundant element on Earth, and the proof is that you are currently immersed in it. Almost 80% of the air we breathe is nitrogen. So, under standard conditions, nitrogen is a colorless and odorless gas. After oxygen, carbon, and hydrogen, nitrogen is the 4th most abundant element in our bodies. It makes about 3% of them. It is present in particular in amino acids, big compounds that are incorporated into proteins. Nitrogen is also vital to plants, and you find some in nitrates and ammonia. Nitrates are compounds that nitrogen forms with oxygen, and ammonia with hydrogen. Both are important fertilizers for plants. We are reaching number 8, oxygen, which, as you know, is another crucial ingredient of life. There is oxygen in the air, about 20%, in our bodies, and also in the ground. It would be easy to think of oxygen just as a gas, because we breathe some. In reality, oxygen also forms oxides with many other elements. So much so that about half the Earth's crust consists of oxygen by mass. Pure oxygen under atmospheric conditions is a gas, and atoms tend to bind 2 by 2 to form dioxygen, O2. Oxygen can also give water combined with hydrogen and all sorts of oxides, with iron, sulfur, carbon, and in particular in the Earth's crust with silicon. Obviously, we need oxygen to breathe. What we call breathing is ultimately a chemical reaction. Oxygen reacts with molecules derived from food. This produces energy that we use, and a main waste product, which is carbon dioxide, which we expel. To continually extract this energy from organic molecules, living beings need to breathe continuously or almost continuously. We need a constant supply of oxygen, and this is what our lungs provide to our bodies. I told you that when it is pure, oxygen comes in pairs of oxygen atoms, dioxygen, or O2. But oxygen also has another form in the atmosphere, with 3 atoms, O3, which is also known as ozone. Ozone is an allotrope of oxygen. You remember what allotropes are? A different form taken by an element under the same conditions, a different arrangement of atoms. Under the form of ozone, oxygen also protects life on Earth, because ozone has a strong capacity to absorb ultraviolet radiation. I already told you a lot about oxygen in previous stories. So for now, let's move on to our next element, number 9, fluorine. As all the elements I have told you about until now, fluorine is the first of its group, and the group it heads is called halogens. Apart from fluorine, halogens include chlorine, bromine, iodine, and other bigger atoms. These elements, these atoms, have 7 electrons on their outermost electronic shell, 7 out of 8 possible slots, and this makes them highly reactive. They really want to attract another electron. Like lithium, we saw earlier, really wants to give up its 3rd electron. So fluorine tends to react with all other elements except noble gases like helium or neon that are inert. Under standard conditions, fluorine is a gas that is highly toxic. It is toxic due to its reactivity. When it comes into contact with moisture, with water, it combines with oxygen and hydrogen. The compound it makes with hydrogen is a powerful acid. It also reacts with the skin, producing burns that could even turn to frostbites if fluorine is liquid. But don't worry too much about it. Only a bad manipulation of chemicals could make you breathe fluorine, because it cannot stay long as a gas in the atmosphere, since it reacts immediately with anything. There is a good amount of fluorine on Earth. It is number 13 among elements in terms of terrestrial abundance, but it is found as a mineral in combination with other elements like fluorite with a T, which is the association of fluorine with calcium. We are reaching element number 10, neon, and with it we are completing a little cycle. Because you remember that neon is the 2nd noble gas the one that comes after helium in the noble gases family. Its outermost electronic shell is full with 8 electrons, so like helium, neon is uninterested in reacting with other elements. Neon is a good example of how elements are not evenly distributed in the solar system or in the galaxy. Neon is actually very common in the universe. It comes 5th in abundance after hydrogen, helium, oxygen and carbon. But on Earth, there's barely any of it. It is found only as traces in the air. So how is it that there is so little on Earth? This is so because neon is very volatile, and it forms no compounds that would fix it to solids like nitrogen or oxygen. So it is believed that almost all neon in the early solar system escaped from the protoplanets that formed near the Sun under the warmth of this new star, including all the rocky planets from Mercury to Mars, which includes Earth. This neon went far to the periphery, beyond Jupiter, where it is rather common, rather abundant, whereas we only have traces of neon on Earth. One use of neon is for lighting. You know about neon signs that were popular in the 20th century as commercial signs. They tend to disappear and be replaced with LEDs that imitate them. But neon signs use neon and electricity to produce light. Inside a neon tube or a neon lamp, neon and other gases are imprisoned at a low pressure and with 2 electrodes. When sufficient current is supplied between the electrodes, the gas produces a luminous glow, and this is how neon lamps or tubes work. Element number 11 is sodium, the second alkali metal after lithium, and another rather common element on Earth, the 6th most abundant. You remember lithium was very reactive with its single electron on its outer shell of electrons. And sodium has the same characteristic. A first shell, a first layer with 2 electrons, which is full, another one with 8 electrons, which is also full, and 1 single electron on the third, which can easily be given away by the sodium atom. So sodium is not found pure, but combined with other elements, often under the form of salt. But what is a salt, by the way? There is a common usage meaning of salt, as in table salt, the mineral that can be added to our food. This table salt is sodium chloride, a compound made of the same number of atoms of sodium and chloride. This type of compound is called Ionic compound, and it could easily be confused with a molecule, but it is not really one. A molecule is an association, a group, between atoms that share their electrons. These atoms are chemically bound. An ionic compound is something else. It is held together by electrostatic forces. In other terms, it is a compound of ions. ions are atoms or molecules that have a difference between their number of protons and electrons, which makes them electrically charged, positively or negatively. For example, in the case of sodium chloride, table salt, we have atoms of sodium with their 11th electron that could easily be given away, and we have the same number of atoms of chloride with 17 electrons. They just miss one to complete their outer shell. So chlorine atoms will steal one electron from sodium atoms, making them negatively charged, whereas sodium atoms with one missing electron become positively charged. And these two types of ions attract each other because of their opposite electric charges. As they come together, they create a well-organized structure, a crystalline structure, in which all the ions replicate the same arrangement. It is orderly. And electrostatic forces, in this case also called ionic bonding, keeps the structure together. So these are not molecules. Actually, an ionic compound can be made of atoms that have opposite charges, or of molecules that have opposite electric charges too, and adopt this structure. In chemistry, a salt is any chemical compound made of ions, positively and negatively charged. As a result of their opposite charges, it has no net electrical charge. Positive and negative ions cancel each other. So table salt is a salt in chemical terms, but there are many more possible chemical salts. Let's advance to element 12, magnesium, the second alkaline earth metal after beryllium. I told you earlier that beryllium was rare in the universe and on Earth, because it got quickly depleted after its formation in stars. Magnesium doesn't have the same problem. It is produced in large aging stars, when they have consumed a big part of their hydrogen reserves, and they start to fuse heavier nuclei. In such stars, the addition of 3 helium nuclei to 1 carbon nucleus gives a nucleus with 12 protons, 3 times 2 from helium atoms, and 6 with carbon. And we get a new magnesium nucleus. This happens by the end of the life cycle of large stars that end in a supernova, which expels all this new magnesium into the interstellar medium, where it can serve, it can be recycled into a new star system. So, like for all other heavier elements, from beryllium with atomic number 4 to the heaviest elements on the periodic table, the magnesium atoms we have on Earth didn't form at the start of our universe's expansion with the Big Bang. They formed later, a few billion years later probably, in stars that died and whose material was recycled to form the solar system. Magnesium is a metal, but the term metal is a bit like salt. Its definition may depend on the context. So, what is a metal exactly? Here again there is the everyday, common definition. What we call metal is any material that conducts electricity and heat that shows a lustrous appearance when it is polished or broken, and generally metals are relatively heavy compared with other materials. So we kind of know intuitively what is metal and what is not in our daily lives. Most of the time we expect to find metals in a solid state at room temperature. But we also know that there are exceptions to this. For example, mercury is liquid, and sometimes we use metal objects like aluminium ladders that are surprisingly light, but aluminium is a metal. Physics and chemistry need more precise definition. In physics, a metal is any substance, not necessarily an element. It can be a combination of elements, like an alloy, any material or substance that is capable of conducting electricity when there is no heat at all, at absolute zero. And this definition can give counterintuitive results. All current metals, iron, copper, gold, etc., remain metals under this definition. But in some conditions, with the right pressure, plenty of elements can become metallic. For example, hydrogen. Inside big gas planets like Jupiter or Saturn, it is believed that hydrogen in the deeper layers of these planets is pressurized enough to become metallic, meaning essentially that it can conduct electricity. Sodium is regarded as a metal, but it can lose its metallic property if exposed to extreme pressures above 2 million times atmospheric pressure. In that case, it ceases to conduct electricity. But at even higher pressures, it is theorized that it should get it back and become a metal again. So, based on this definition, metal or metallic is as much a state, a property of a material in certain conditions, as it is a characteristic. This tends to blur the frontier between metals and non-metals. And then there is yet another definition, which is the one from astrophysics. The term metal in astrophysics is cast more widely to refer to all elements in a star that are heavier than helium. That is to say, basically, all elements except hydrogen and helium. This definition contradicts the common definitions of chemistry and physics. In astrophysics, elements like carbon, oxygen, or nitrogen become metals, which they are not in chemistry. So, as you understand, it depends on the definition. The one from astrophysics is probably too broad for other disciplines. It makes sense in astronomy because it's about the genesis of elements in stars. But whatever definition of metal we choose, magnesium falls into this category. It conducts electricity at standard conditions and also at absolute zero. Another aspect of magnesium is its importance for life. Alongside the elements that really form the main building materials of our bodies, oxygen, carbon, hydrogen, magnesium is one of the many elements that are present in small quantities but are essential to life. It is in every cell and in hundreds of enzymes. Enzymes are big proteins that act as catalysts to chemical reactions in our bodies. We absolutely need them to ensure our metabolism works correctly. And these enzymes require magnesium ions to function. For plants, magnesium is necessary to synthesize chlorophyll, which is essential to photosynthesis. So here again, an essential element to life as we know it. We have just explored 12 elements out of more than 100, and we will continue our review of the elements and some of the laws of physics and chemistry that help understand how they work next time. In the second part, we will resume with element number 13, aluminium, another metal. But for now, we have reached the end of our story for tonight. You can now let go and fall asleep, or pick another story from my library. I'll be back soon, and in the meantime, sleep well, sweet dreams, au revoir.